Let's get started again. Question. First question. In this particular wave function, अब assignments क्या बात छोड़ दें, खत्म हो गई. In this particular wave function, what's the average position of the particle? What's the average location of the particle? 0. At x equals 0, at the center of the well, the probability density is 0, but the average location is also 0. But remember that the average is misleading. You can have a dice, you throw the dice, you get 1, 2, 3, 4, 5, 6, it's an equal probability distribution, but the average is 3.5. You will never see 3.5. So the average is nevertheless 0, average location, but the probability density at this average location can still be 0. And if you would like to find out where is the maximum probability density, how would you find out the maximum? You would just take the modulus squared of psi 2, modulus squared, and take the derivative with respect to x, equate this to 0, and solve for x. This is how you find the maximum or minimum of a function, and I'm sure you've done this already. So you should be well versed with finding the location of the maximum probability density. Alright? By the way, you can get the minimum as well with this procedure. Okay? So this gives you the maximum as well as the minimum, so you'll have to take the second derivative to determine whether it's a maximum or a minimum. Alright, so if I were to plot the wave function for n equals 10, so this will have nodes at the walls, and there will be 8 nodes inside, 9 nodes inside the well. So if I just try to draw this, this might look something like this. Nodes, or 5.5 cycles fit into this, right? And if I were to draw the probability density of corresponding to this wave function, this is what the probability density is going to look like. Outside the well, of course, it's 0. So the graininess of the wave function decreases. Which means it's, so if you stare at this wave function from a far distance, it doesn't look like wiggly. Because the changes are so rapid that it looks less wiggly. If I put n equals 100 here, if I were to put n equals 100, then the wiggles will become so rapid in space that if I were to ask you the question, what's the probability of locating the particle in 1/3 of this region? It would be 1 by 3. Because the spacing is so equal. Alright, so if you increase the value of n, the graininess of the wave function becomes less and less observable. Because if you would like to see this graininess, do you understand the meaning of the word graininess? Graininess ka the meaning of graininess is finesse, but finesse is a more difficult word. So if you would like to observe undulations, or you'd like to observe waves, you'd like to see that it's going up, then it's coming down, then going up. You would like to have a span of observation that is smaller than the wavelength of this wave. If your observation does not have a fine scale or a resolution that is good enough to observe this wave nature, then you will not be able to see it. So if you would like to observe this wave, now these are subtle points, please pay attention. Excuse me. You won't find these explained in this manner in any textbook. So if you would like to observe this wave nature, this graininess, and the probability density is going up, it's going down, there are some regions where there is little probability of finding the particle, you'll have to make an observation on a length scale that is smaller than the size of the wave. Alright? Otherwise, you will not be able to capture the wave like ebb and flow of this wave. You will not be able to see it go up and down. If you would like to see it go up and down, you would like to have a resolution that is finer than the scale of the wave. So if you have something written on this piece of paper, if you're observing this from a distance, you'll not be able to see the individual lettering. You will just see a blob of ink. But if you come closer to it, you will be able to see the individual lettering if you have a resolution that's good enough. So if you would like to see this wave nature, if you would like to see quantum mechanics at work, or the breaking of the isotropy of space, or you would like to see the nodes and the antinodes, then you will have to make an observation that is smaller in space. You will have to be able to distinguish a crest from a trough. Okay? So if n becomes really large, it becomes more and more difficult to observe this quantumness. Let me call it this graininess as quantumness. So it becomes difficult to observe the quantumness. So n equals large corresponds to our classical word. We are not able to see this graininess or quantumness because for the systems that we're dealing with, they are macroscopic systems, they are large systems. The large systems and n is really large. So we're not able to observe this quantumness. Okay? Now what I would like to point out is another thing. What is meant by n equals 1, n equals 2, n equals 3? We know that these correspond to different wave functions. But if I have a particle, I put it inside the well, what is its n going to be? Right? I've given you mathematical solutions to the wave function and how these wave functions look like and how the probability density functions look like. Now, how in this world am I going to figure out that if I put a single particle, an electron, inside a well, what would its n be? So I would actually like to determine an answer to the question, what's the wave function of the particle if I just put it inside the well? Whether it's psi 1, psi 2, psi 3, what n is it going to acquire? What n is it going to possess? So every system in nature would like to lower its energy. Like us human beings who just like to settle, reside at one stationary place and relax, every system in this world would like to lower its energy and come to a ground state. But we have not yet taken into account energy in this problem. So we'd like to find out what does energy have to do with these wave functions. Okay? And the answer actually lies in this factor over here. So I'm not going to so I have to answer this question, but let me do another thing before I can do that. is my infinite well. This is x equals 0, L by 2 minus L by 2. What's the length of the well? L. Is the potential energy landscape, which means how the potential energy changes with space, is it symmetric with respect to x? Yes, it is symmetric. If I put a mirror plane here, if I were to put a mirror plane here, then this picture is exactly the mirror image of the picture to the other side. So this is a symmetric potential landscape. When I have a symmetric potential energy function, the wave functions, which I've written over here, this is cosine, which is an even function of space. This is sine, which is an odd function of space. The wave functions are even or odd if the potential energy is symmetric. Okay? One thing. The second thing is that what's special about defining this to be the origin of my x-axis? There's nothing special about it. I can call this the origin of the x-axis. I can call this the origin of the x-axis. The physics doesn't change. Alright? It should not change at all. The mathematics should not change. And the picture of the wave function shouldn't change at all. Okay, because I'm just relabeling my axis. I'm calling L by 2 as 0. That's fine. The only thing that I would like to keep consistent is the length of this well. I would like to keep the length of the well L. By the way, something is coming to my mind. When we look at the Bohr's model, we also had standing waves. In the circumference of this orbit, there was an integral number of half wavelengths, or wavelengths in that particular case. Now within the infinite well, we have an integral number of half wavelengths. So this is a standing wave, by the way, but a special kind of standing wave. Anyway, if I were to redefine this mathematical slant of this problem by defining this to be x equals 0, and this to be x equals L, then the physics of this problem should remain unchanged. It shouldn't change at all because I'm just redefining the axes. Alright, so this is what you will conventionally find in textbooks, and you will find this kind of description in survey. The only thing was that I want you to make the problem look more complicated by making it go from minus L to plus L by 2, and you get these two kinds of wave functions, because this, looking at a complicated problem at first go will actually give you more confidence. Now if I were to take this to be x equals 0 and this to be L, I can find out, I can solve the Schrödinger equation again, subject to similar, effectively similar boundary conditions. For example, inside the wave function, inside the well, this is my wave function. At x equals 0, the wave function must go to 0. So I put this equal to 0. X equals 0, this becomes 1. X equals 0, this becomes 1. So a plus b equals 0. So this is an easier equation to solve. I get b equals minus a. Always. Okay? And then if I look at this boundary, 0 equals the wave function and x equals L, I get a e I k L. B is now minus a, so minus e minus I k L. So this becomes 2 iota a sine of KL equals 0. Okay? Now A cannot be equal to 0 because if A equals 0, everything just disappears. KL has to be 0, which means that KL has to be pi, 2 pi, 3 pi, 4 pi. So KL is n pi, where n can be even or it can be odd. Okay? Now KL is equal to n pi. N can be even or odd. It could be any whole number. So these conditions, KL equals n pi and B equals minus A, are going to provide you with the solution of the Schrodinger equation with this reference axis. And let me see whether it matches the solution that we've already found. Yes, they do. Indeed, they do. So now I have the solution to my Schrodinger equation is A EIKX. K is now n pi x over L minus E minus I n pi x over L. This is my wave function inside the well. This gives me 2 iota A sine of n pi x over L, where n is 1, 2, 3, and so on. It's a simpler solution. It does not break up the problem into even and odd parts because it's not symmetric with respect to our definition of the axis. But it's a simpler solution, and this is also going to give us identical wave functions. So I can just renormalize this again, and I will get the same result. 2 over L under root with an iota, which is inconsequential, sine of n pi x over L. Let me check the n equals 1 state. If n equals 1, this is sine pi x over L. This is now L, this is 0. At x equals L, I get n pi, which is 0, 0. At x equals L by 2, which is half in the middle of the well, I get n pi by 2, pi by 2, which is 1. So I get the sine function, which is maximum here. I get the same wave function as I previously drawn. If I put n equals to I get the same wave function as I previously drawn. N equals 3 will give me the same wave function, and so on. Alright? So this is the solution to my Schrodinger equation inside the well. This is the wave function. Let me write this down in glorious form, in box form, ignoring the iota factor. Any questions up to this point? And then we're going to talk about energies. Anyone else with a question first? Anyone who has never asked a question? Would anyone like to ask a question? Yes.
Sir, why is space like this? And why is it probability different at different points in space?
I'm going to answer that question in a minute, okay? When I talk about energies. Yes.
Sir, why is iota inconsequential? How is it a
Iota is inconsequential because if I have function psi, something else with it, say a sine of n pi x over L. If I take the modulus squared of this function, this gives me minus iota times a star times this multiplied by a iota a sine of this. Minus iota into iota gives me 1. So it doesn't matter. And the probability densities are what really matter. That's why it's inconsequential. And iota is really e raised to power minus iota pi by 2. Okay? Yes?
Sir, in that we got a minus sign curve and that got a plus sign curve.
It doesn't matter. The minus sign is also a global phase, ei5. And the probability density doesn't change. Any more questions? Now we're going to talk about energies inside the infinite well. Why would I like to talk about energies? Excuse me. I would like to talk about energies because I would like to answer the question is that if I have a particle, I put it inside an infinite well, then which wave function will it acquire? What's going to be the wave function? Will it go into n equals 1 wave function, n equals 2 wave function, n equals 3, n equals 100? It would actually like to go to the lowest energy states. So I would like to associate energies with the wave functions. Okay? So what I need to know is something really simple. I've already defined my k. When we solve the Schrodinger equation, which is given by this, minus h bar squared 2m d squared dx squared psi x equals e psi x. I took this 2m over h bar squared to the other side and I defined that to be equal to k squared. So my k is really 2m e over h bar and there's a square root over 2m e. So it's 2m e over h bar squared over all. So this is my k. Alright. So what is my E? My E is actually dependent upon my K. K is telling me the energy of the particle. So if I know K, I know the energy of the particle. So this means that my E equals h bar squared K squared over 2m. Which is exactly similar to P squared over 2m. According to the de Broglie relationship. So this is my energy. But what about my K? K, we know, is this factor over here. N pi over L. Let's talk about this formulation of the problem. This is my K, N pi over L. Okay? Where do I have? This is my K. My K is actually n pi over L, where n is 1, 2, 3 and so on. So now if my K is, now what's happening to K? Can K take up any value it likes? Is it continuously varying? Can K be anything? No. There are constraints on K. It can be pi by L, 2 pi by L, 3 pi by L, 4 pi by L. It cannot be 2.5 pi by L. It cannot be 2.2 pi by L. Only certain specific values of K are allowed. In other words, the word that we use is that K is quantized. And why has K been quantized? K has been quantized because we have a bound system. Because we are restricting the space in which the particle can exist. We have a well, and we are destining the particle to exist only inside the well. We are trapping it from the left and from the right. We are binding it, or we are confining the particle. Whenever we confine a particle, which means that we only allow it to exist within a certain volume of space, K's become quantized. If we have a free particle, when we solve the Schrodinger equation for a free particle, K could be anything. There is no restriction on K. A free particle which is free, unbound, can have any K, whatever it desires. It depends upon the energy of the particle. But if we confine the particle, its K becomes quantized. And when K becomes quantized, this E becomes quantized. So energy is quantized, E is quantized, K is quantized, E is quantized. And we can come up with a general principle of physics which permeates all of physics, all of nanotechnology, all of modern electronics, all of quantum biology, all of quantum computing. Most of physics that I can think of is embodied within this simple adage or statement that confinement leads to quantization. Whenever you confine a particle, its energy becomes quantized. That's what happens inside an atom. You're confining the electron to remain within the atom. Its energy must be quantized. You get orbits, orbitals. All of the elements, all of the molecules have electrons which are in quantized orbits. All of the light you see from different incandescent sources, lasers, sun, everything comprises light coming from quantized sources. And we have quantization because of confinement. एक मिनट. And we know how K is quantized. K is quantized according to this recipe. So the energy is also quantized. The energy becomes h bar squared. K square is n squared pi squared over 2nl squared. Excuse me, please, just 20 more minutes to go. Eight, sorry? Why? So this is the energy. The energy has now been quantized. Now the nice thing is, what's the minimum value of n?
1.
1. So when m equals 1, the wave function is sine pi x by L. It takes this nice form. This is the wave function. This is the probability density. Of course, I have to put axis with this, but I'm being expedient here. And the energy of this, if an electron or a particle inside the well is in this wave function, is in this state, then its energy is going to be h bar square pi square 2ml squared. So its energy, and I'd like to put a small 1 with this to show that this is n equals 1. So I can put an n here. Its energy is going to be h bar square pi square 2ml squared. Let's call it E naught. Now this is the minimum energy of the particle. And this wave function is also called a state. It can also be written as psi 1 ket psi 1. This is also a quantum state. Its energy, and if the particle is in this state, its energy is E naught. And it's not zero. This state is called the ground state of the particle. And the ground state energy is never ever going to be equal to 0. There has to be some minimum energy of the particle. Why is that? Can we come up with an argument, another kind of argument? Now we've looked at the mathematics. We've seen that the minimum energy has to be E naught. So could you come up with an argument of why, some other argument, an alternative paradigm of thinking, why should this E naught be not non-zero? Yes? No, why? You can have zero energy particles. Yes? It's against the uncertainty principle. Why? Is that your answer as well? Okay, let me first see an explanation for that answer. Okay, I understand what you're trying. If you see, in a well, this is the length of the well. What's the uncertainty in the position of the well? It's of the order of L. So the uncertainty in the position of the well is of the order of L. So delta P has to be of the order of h bar over L. Which means the minimum momentum should be h bar over L. Minimum. Which means that the minimum momentum has to be h bar over L. The uncertainty in the momentum is bigger than the uncertainty in the momentum, if anything is to make sense. Which means that the energy has to be greater than a minimum value. And this is h bar squared over 2ml squared. If you ignore this pi square factor, why do you ignore it? Because we're just looking at an inequality here. This satisfies this inequality. Energy is bound from the minimum side. It has to be some minimum, non-zero minimum, so that the uncertainty principle holds true. And if I make L shorter, if I confine the particle to even shorter and shorter distances, the ground state energy goes up. If this confinement is really tight, which means instead of 10 nanometers, I have a 1 nanometer long nano chain, nano ribbon, in which I'm confining the particle, the minimum ground state energy is going to go up. The other thing that we observe is, this is the ground state. So the particle, if it left on its own and everything, temperature is really, really small, so that everything is settling down to its ground state, the particle will be in the n equals 1 state. That's what the particle would like to be in. But there are other states as well above it, which are called the excited states. So in this infinite well is actually an epitome or a model for atoms, for molecules, for the harmonic oscillator. You understand this, you almost understand 80% of all of quantum mechanics at the freshman level. So, so what's the energy, excuse me, what's the energy of the particle when it possesses the nth wave function? It's going to be n squared times E naught. So now if I would like to make an energy level diagram inside the well, this axis is my energy axis. The minimum energy of the particle is E naught, which is inversely proportional to the length of the well. The next energy is let me call this E1 because n equals 1. Okay, sorry. Let's call this E1. Let's not call it E naught because n I would like it to be 1. So the minimum energy is E naught. The next energy of the first excited state is, now this is 2 squared, this is 4 times E1. The next energy level is going to be 3 squared E1, 9 E1. The next energy level is going to be 16 times E1. So the energy manifold is now quantized because of confinement. If I put a single electron inside the system and let everything go to its ground state, everything is cool, there is no bombardment, no excitement whatsoever, the temperature is really down, the electron, if I'm talking about electron, it's going to go into the ground state. It's going to come here. Let me just draw a picture of the electron. A naive picture, and its wave function is going to be given by what we already have. Then I give it some energy. Suppose a photon comes in. Here comes a photon which has some precise amount of energy, and that energy is 4E1 minus E1, which is 3 times E1. Then that photon will give off all its energy to the system, and the electron will be promoted to the next excited state. It will come here. But this energy has to be precise. If it's not precise, then the photon will not be absorbed, it will just transmit through the system. Because there is no energy level in between. These are all forbidden energy states. Only the electron can gain energies in precise steps. Now if an electron is here, it has been given energy, or it has been given energy, it can also fall between levels and emit photons. And the energy of this photon will exactly match the energy gap between two quantized levels. So we're going to look at time evolution, how these states change with time in the next lecture, and we're going to look at tunneling. Yes, thanks a lot.